We're looking at problem 20 on page 673, chi-square test. What it looks like is that we have 3 different years. So each of those 3 years would be a different population. Good. So that means when I'm doing this chi-square test, I'm going to have a null hypothesis that is based on the fact that I have different populations. So I'm going to say that the proportion of voters affiliated with different parties is constant or equal for the 3 different years, specifically 2003, 2004, 2005. Okay, we'll keep trying. Okay, once we have that much, I think the next thing we're going to need is an alternate hypothesis, which for chi-square you can keep your alternate hypothesis very simple. Well, if I can get it to work. The alternate hypothesis is just that the proportion of voters affiliated with different parties differs for at least 1 year. It's important to remember that when we're dealing with chi-square, we're just saying, is there any difference between any of the different populations? So it will not necessarily, if 2 of the 3 years happen to be the same, it's not going to pick up on that. It's just going to say, hey, there's a difference somewhere. So assumptions for chi-square is that I have in this case, since I have different populations, I need independent random samples. So I have independent random samples of the population of interest of voters for my 3 different years, which is given. And also I need to know, are expected counts greater than or equal to 5? Okay. And the test I'm going to be going for here is a chi-square test of homogeneity. Anybody got questions so far? Unfortunately, to get those assumptions checked, I'm going to need to go ahead and run this test. That's just the way the calculator works. So we're going to have to go to second matrix. I'm going to edit matrix A, and I'm going to put my table of data I have in the book in the calculator. It looks like I have 4 rows and 3 columns of data, so I'm going to need a 4x3 matrix. And if you guess wrong, you can always change the numbers to get it to make it the right size. So 397, 301, just type in the numbers. It gives us, having trouble, 301, 458, and 60. Get my next column, and we'll get this in just a second. Once you get everything in your matrix, then you're just ready to go to perform your chi-square test. Oh my goodness, I'm having difficulty. Once we have the data typed in the calculator, then we are ready to go to stat, test. It does not matter if it's a test for homogeneity or test of independence. That is still option C, the chi-square test. So chi-square test. I know we don't have expected values in B, but the calculator is magical because once I do calculate, if I go back to matrix and edit matrix B, then those are my expected counts. So I'm going to say, in this case, yes. And usually what I need to put is that you can see the table. So you need to probably write a version of your table with those expected counts in there for the purpose of doing a frappy, but if it's multiple choice, it's just good to know that, hey, all of my expected counts are greater than 5. And to get these expected counts, once again, we can just go to matrix, and we can edit matrix B, and it's done all the expected counts for you. Now, in the event you need, well, any questions there? Hey, so since I know my assumptions are good, I'm going to go back to my test again. Well, the right test. Stat test, option C, chi-square. And this time I'm going to pay attention to what it tells me since I know my assumptions are good. And what it tells me is that I have a chi-square value of 26.17. That's a pretty small chi-square value. And it has a degrees of freedom of 6. And the probability that my chi-square value is greater than 216.16, or 0.17, sorry. Would that mean the degrees of freedom is 0.000206. So that is a really small probability of having a chi-square value that exceeds that amount for this particular situation. Now, as far as where the degrees of freedom comes from, degrees of freedom for a chi-square table is the number of rows minus 1 times columns minus 1. So in this case, I had a 4 by 3, so that would have been 4 minus 1 rows, and that would have been columns would have been 3 minus 1. So that would have been 3 times 2. That's where the 6 comes from for the degree of freedom. There's your chi-square value. So since my p-value of 0.0002 is less than, we don't technically have an alpha, but we'll make one real quick. We'll say an alpha of 0.05. That's pretty standard. I'm going to reject h sub 0, which means we find statistically significant evidence that the proportions of voters affiliated with different parties changes, or we'll just say differs, between the years 2003, 2004, and 2005. Now, it is not an absolute necessity to discuss this every time, but it's a good thing to say, to think about where are your differences the largest. And one way you can do this is you can go back here and look at your matrix again, your expected counts, and you can basically say, where were these expected counts off the most? So, for example, it looks like in general we had, for the year 2005, I had more other, I guess, third party than I would have expected for 2005, comparing this 52 to my original 60. It also looks like that was one of my discrepancy of 8. And you can just kind of look and see where are your biggest discrepancies. It looks like the number of independents were substantially different from what you would have expected to be if they were, it seems to be, have dropped substantially, be a lot less in 2004 than it was in 5 and 3. So you can just kind of compare the original data to what your expected values were for B to see where some of the biggest differences were. That's something to be able to do. In a 2x2 table, it's not a two-way table. It's not always easy to find one that jumps out. Goodness of fit, it's usually pretty easy to find one or two categories that are really off.